discussing about the photoelectric effect. So I told you that when light falls on the surface of some of the elements, when light falls on the surface of some of the elements, then the valence electrons of those elements, they are being ejected. Okay. So what happens now? This electron which is there, it goes. And this is light. I can write here now 8 nu, because it is coming with a frequency of nu. So this ejected electron is called photoelectron. Now, what is the condition? When this type of electron will go, when we find the energy associated with this light. The energy associated with the light, it should be equivalent to the energy, binding energy of the electron. Binding energy of the electron. When it is equal, the electron gets alighted from the surface, and after that, if you find the energy is more, then this electron moves away. This type of phenomenon is called photoelectric effect, and the electron which is ejected is called photoelectron. Now the condition is that, is it a general phenomenon of all the metals? No. It is only shown by only few metals. So what should be the condition? The condition is that we know electrons remain in the orbit of an atom. And these electrons, they remain in the orbit because there is a balancing force by the centrifugal force occurred due to the movement of the circular movement of the electron and the attraction of the nucleus. So when this attraction of the nucleus is less, that is when the binding energy of the electron is less, then only those type of electron can go out. So now, when the energy of the electron can be less, binding energy of the electron can be less only when these electrons are far away from the nucleus. If the electrons are far away from the nucleus, then only the light, visible light, when it falls on it, it can remove that electron. So when the electron can be far away from the nucleus, it is only possible if the size of the atom is large. So little bit of information you know about the periodic table. That in periodic table, when you go down the group, the sizes of the atom increases. And when you move from left to right of the periodic table, the size of the atom decreases. So where can you get the larger size of atoms? Larger size of atoms are always found in the first group. From first group, whenever we move up to the group 18, the atomic size decreases. So larger, in each period, larger atom is always found in the first group. Now you want to get larger or largest, then you have to go down the group below. So there are 3 or 4 such metals are there which shows photoelectric effect. They are potassium, cesium, okay, then rubidium, this type of elements. So if photoelectric effect is being shown by larger atoms like potassium, rubidium, cesium. We are not talking about francium because that is radioactive. So what we will write now here? Only few metals such as potassium, rubidium, or cesium exhibit photoelectric. Why? Because they are larger in size and their valence electrons are far away from the nucleus, and in that case those electrons can be easily knocked out. What we can write now? It is because these atoms are larger in size, and so their valence electrons have lesser binding energy and can be knocked out. This is not very good English. And can be ejected. By photons of the incident light.
Excuse me, sir. Sir?
Okay. So now,
Excuse me, sir.
Yes.
Do nonmetals exhibit photoelectric effect?
Huh?
Do nonmetals
What?
exhibit photoelectric effect?
Non-metals lie on the right hand side of the periodic table. See, when I will go to, after structure of atom, I will go to periodic classification, then you will understand why non-metals, not only metals, dear. See, there are 118 elements are there. Out of 118 elements, near about 12 or 13 elements are not 12, around near about 20 elements are there which are non-metals. Rest of them are metals. So in that case, out of so many metals, Near about 100, only 3 shows. So when we'll go to the periodic table, then you'll be able to understand why most of the metals and not a single non-metal show photoelectric effect, because it depends upon their size. See,
Okay, sir.
when you stay at home, there are many things which you cannot do. You cannot go out of the house at any moment you wish, because there is some restrictions are there. But suppose after class 12 you went and stay in faraway place from Shillong, that there too you can go out anytime. Why? Because our parents are not there. They are very far from you. They cannot control your movement. Same is the case. Group 1 contains, in each period, group 1 contains the larger size of metals. So when you go from each period, there are, this group 1 only contains the larger atom. And when you go down the group, their largeness increases. So comparatively, the larger size of atoms are always there at the bottom of the group 1. These are potassium, rubidium, and cesium. Below cesium also you have another element is there, is called francium. Francium is radioactive. All right, and its stability is very, very less. Because of that, I did not include francium here. Okay.
Thank you, sir.
Somehow, because of today, I have around 15 minutes. I have late. I finished my lunch only at 3:35. Classes I had up to 3:10. So anyway, okay. Now let us see. In this case, so I told you, when when the energy of this photon is equal to the energy of the electron, this electron will come and stay out. It will be here because it could overcome the attraction. But if the energy is more, so rest of the thing will convert it into the kinetic energy of the electron. I told you, suppose you find you came to your home, you have done some mischief outside, you find your either your mother or father or anyone guardian, he has got very angry with you. You, moment you enter the door, you again come out and stay outside. And after that, if you find that they are aggressively coming towards you, then you rip that place. So see, when you subject the light or having photon equal to the energy of this electron, it will just come and stay here. But if the energy of the photon is more, then it will be converted into is kinetic energy. All right. Now, so I write if the light containing photon of high frequency falls on metal surface. Okay, what will happen now? A part of the energy is used to free the electron from the atom. It overcomes the attraction of nucleus. This energy is called work This energy is called photoelectric work function, and we mention as the bit 0. Why you call it work function? Because the functioning of the photoelectric starts. Because of that, we call it work. Okay. Then second is what? See, I don't know how to give examples. Say this is a mango tree, and this is a mint. So, but you are growing in town, no, you have no idea. In our we have grown up in suburban and villages. So before the mango has ripened, we used to pluck it. When most of the mangoes were nearby the road only. So we throw it with the stone. The stone comes. Ultimately, it hits. Okay. So suppose this is the one. The stone come and hit the mango. So if the energy of the stone is equal to the binding energy by which the mango is being held on the branch, it will detach. I'm not saying because by virtue of gravity it will fall down. So we remove that concept of virtue of gravity. It will detach. Now, the speed by which you have thrown, if it is more, that mango will not, by virtue of gravity, will not fall here. It will fly. It will fall away from the plant. So it is like this. So now the second part. First part is that it absorbs a minimum amount of energy to dislodge the electron from the orbit, or it comes out of there. Second, rest of the energy is used in giving kinetic energy to the photoelectron. Okay. So let me write here. Let the frequency of photoelectron is nu.
Sir,
Yes.
can you please repeat again? Can you please dictate B?
Hmm?
Can you
Which
please
one?
dictate B? I can't see the
Rest of
board.
the energy is used. Okay, I'll write down here. Rest of the energy of photo is used in giving kinetic energy to the photoelectron. Okay, kinetic energy to the photoelectron. So let me write here. Let the frequency of photoelectron equal to nu. Therefore, the energy associated with the photoelectron, okay, say E will be equal to what? We know it will be equal to h nu. So as per this statement that we expression we have given, what we can write that energy of the photon h nu equal to what is being divided into two parts. First, it takes out the electron from the atom, that you call it work function. The rest of it is being converted into kinetic energy. So I'll write now here work function plus kinetic energy of photon. Okay. So I can write here, or h nu is equal to W0 and equal to what? You know what is the value of kinetic energy? Half mv square, where m is equal to mass of electron. See, all electron has the same mass, so I need not write it as photoelectron. And what is v? Is the velocity of photoelectron, or you can write electron. So now let me write it like this. H nu is equal to is equal to W0 and half mv square we have written na. So now see, this is also energy. Work function is also energy or not? So what should I write? Let me write here. Let nu 0 is the threshold energy. Threshold energy means what? Optimum energy to take out the electron from the shell. That is called threshold energy. That nu 0 is the threshold energy. Therefore, W0 is equal to h nu 0. So in that case, see, if I write it in this way, 1, all right? So I can write now this is equal to h nu is equal to h nu 0 plus half mv square. So this will be the equation. Or I can write in other way also. If I subtract in this way, so I can take, okay, I will not go for shortcut. Huh? No, too much shortcut is not good. Sometimes you get confused. Or I can write what? I can take h common, h nu minus nu 0 is equal to half mv square. So this is equation. Okay. Now again I'm explaining to you. See here. Electron requires minimum amount of energy to overcome the attraction of the nucleus to come out of the orbit. Say electron is here. Electron is here. So when it gets that much amount of energy, then it comes out. It is here. When rest of the, if the energy is more, the rest of the energy is being converted into the kinetic energy. Right? Say you are lying down on the bed. You are supposed to get up early morning, but you find somehow that you do not want to get up. But ultimately, you have so many different types of works are there. So in that case, you get down from the bed, get up from the bed, and after that, you have to gather energy to work. Okay. So what is this here? How much energy is required? It is called work function. Work function. And the amount of energy that is required to remove this electron, W0, is H nu. So we have found that what about the energy that is associated with the electron? Sorry. What about the amount of energy that is associated with the light particle of the light that is called photon? This is being used in two purposes. First is the electron is being taken out, and after that, rest of the electron is energy is being used for movement of the electron. So because of that, we have written H nu is equal to work function, that is W0, plus kinetic energy, that is half mv square. So we have written H nu is equal to W0 plus half mv square. Now we know the work function is nothing but a energy, and energy is associated with the frequency of the radiations, and that is should be the optimum amount of energy. And optimum amount of energy, we call it threshold energy, and for that we have given a symbol of nu 0. So now we can substitute it, and we can get H nu is equal to H nu 0 plus half mv square. So if I shift this term associated with nu in the left hand side, we get H nu minus H nu 0 is equal to half mv square. And ultimately we got the final equation that we have taken H common. So H is taken as a common, nu minus nu 0 is equal to half mv square. Now there are some observations. See, as I told you that you are plucking a fruit from the tree by throwing stone. So in that case, as if that your aim is very good, you can hit each mango with single stone. So to pluck a mango, you require one stone. By throwing one stone, you cannot pluck two mangoes. Okay? And second is that if you want to pluck more mangoes, you have to throw more stones. So these are the two observations. That is, each photon can knock out one photoelectron. That is, for each photoelectron to be knocked out, you require a photon whose energy should be equal or more than nu 0. Okay, so if you throw a small stone, you cannot pluck a small mango, even if it goes and hit it. It will not fall down because it is held tightly in the plant. All right. And second is that if you have taken a stone and you have thrown with a lot of force, mangoes will be plucked. But the extra amount of thrust that the mango got, it will fly to a longer distance. All right. So what we can say? That is the kinetic energy of the photoelectron depends upon the energy of the photon that is associated. And moreover, a single photon whose energy is equal or more than threshold frequency can only remove one electron. That is what you can say. That is, the velocity of the photoelectron is directly proportional to the frequency of the photons. If the energy is less, speed will be less. If the speed is less, kinetic energy will be less. And if the energy of the photon is more, because see, to pluck one electron or more, one electron, the value is fixed because it's a binding energy. So if you have supplied less energy, less than that of binding energy or work function, electron will not go up. You have to supply that fixed amount of energy. So when you supply fixed amount of energy, one electron will come up. But if the energy is more, rest of the energy will be converted into kinetic energy. So in that case, what do you find? The kinetic energy of the photoelectron is directly proportional to what? To the frequency of the light or photon. Second, if you want to remove more electron, one photon cannot. Because each photon for one photoelectron. So if you want to pluck more or if you want to remove more, in that case, you have to supply more photons. And I told you that photon is a particle which is associated with both wave nature and also particle nature. So please remember, the number of photoelectron removed is proportional not to the frequency but to its intensity. If the intensity is more photon, because intensity means what? Photons, not photon, photons more with similar frequency. Photons with the same energy should be more in number. So anything which is more in number, we do not use the term frequency, we use the term intensity. So these are the two important observations of this photoelectric effect. So we'll write now here. One. What one we have learned? That your photon should have, energy of the photon should be equal or more than that of the work function. The energy of the photon to eject electron from the metal surface should be equal or more than work function. Okay, that is, it should have minimum, it should have frequency equal to threshold frequency. Is what? Mu zero. Second, the kinetic energy of the photoelectron is directly proportional to the frequency, that is nu, of the photon, of the incident radiation. Likewise, light is falling, na? Incident radiation. This is the incident radiation. And independent of intensity. Try to understand this one. See, you have to pluck a mango, you have thrown 10 stones. Only one of them won't hit that mango. 9 are wasted. So it does not depend upon how many stones you have thrown. It depends upon the specific stone which is being directed just to the mango. So it is independent of intensity because only one is required. Right, I'll write the third one. I don't want to remove this equation. Okay, so let me remove this one. Third is the number of electrons ejected per second, because it's a question of measurement, is, sorry, again, from the metal surface depends upon the intensity, and intensity means what? Okay, you will write down here if you forget, or brightness, because you are using light or incident radiation. but does not depend upon its frequency.
Sir, can you please dictate point number 3 again?
Point number 3. The number of electrons ejected per second from the metal surface depends upon the intensity within bracket you write or brightness. Close the bracket of incident radiation but does not depend upon its frequency.
Thank you, sir.
Okay, now I want to tell you something. Please remember, we know Einstein is a very famous scientist and he was being awarded Nobel Prize. And Einstein in this world is famous for his theory of relativity. Okay, but try to remember, Einstein got Nobel Prize on photoelectric effect. Initially, he was not working in a science laboratory. When he got this, when he done all this thing, he was a clerk in the patent office. Patent means suppose you have discovered something, then you want to register. So he was acting as a clerk in that office. That time only he has done this experiment. He and this photoelectric effect only has fetched him the Nobel Prize. He did not get a Nobel Prize for his theory of relativity. Okay. So now we'll do numericals. I told you that as the time is very less, we started very late, so we will not be able to do many numericals. If I get time, I'll try to do some numericals for you and I'll still send you. But the whole day I'm having class. Already I have finished 3 classes with this school. Yours is 4th. After you, I will be taking another class for class 2. So time is very, very less for me. So now we'll do a numerical. And my request is that please get calculator. Okay, by the time I write, get the calculator by your side. Because these sums are not difficult, but you have to do a lot of multiplication.
Excuse me, sir.
Yes.
Can you please show how to
Yes. Tell.
Can you please show how to calculate the value of Planck's constant?
Planck's constant value. This calculation you can find only in physics book. In my chemistry book, it is not given here. But value is 6.26 10 to the minus 34 joules second. Okay.
Okay, sir.
All right. So I remove this. When light of 470 nanometer falls on the surface of potassium metal, electrons are emitted. With a velocity of 6.4 into 10 to the power 4 meter second inverse. What is the minimum energy required to remove 1 mole of electrons from potassium metal? Okay, so I have to give you some value. Okay, so now let us see what are the value I should give you. What is the mass? Mass of electron is equal to what? 9.1 into 10 to the power minus 31. 31 kg, I'll write here 34 gram. Okay. I'll write here ME. Then what is the value of H? 6.626. 6.626 or yeah, 6.626. Yeah. Into 10 to the power 34 Joule second. Okay. Now what is, if you want to convert nanometer, 1 nanometer is equal to what? How many meter?
One into 10 to the power minus 9.
Minus what? 10 or 8?
9, sir,
Oh,
minus
let me
9.
check.
1 into 10
Sure.
to the power.
10 to
No,
the power
sir.
minus 9.
Okay. See now, what is the meaning of this? When light of 470 nanometer is the 470 is the wavelength, falls on the surface of potassium metal, electrons are emitted with the velocity of 6.4 10 to the power 4, 6.4 into 10 to the power 4 meters second inverse. What is the minimum amount of energy required to remove 1 mole of electron from potassium metal? See, entire equation that you have written there, this is for only 1 electron. So what you know? We'll write now here. Now see here. What is the minimum amount of energy required? Means what? What is the other name of minimum amount of energy required? Is the work function. So intentionally they have written that work function so that you get confused. If you do not understand theory, I told you, moment you do the numerical, then you understand the theory. So minimum amount of energy required is what? Work function. So I'll write now here. H nu is equal to W0 minus half mv square. Or I can write here, so not plus minus, plus kinetic energy. All right. So what I'll do now, I want to find W0. So W0 is equal to what? H nu minus kinetic energy. See, here the values are so big, so we will not solve it together. We'll solve it separately, and after that we'll subtract. Okay. So now what we'll write now? Let us try to find out kinetic. Kinetic energy is equal to half mv square. See, the mass of the electron is already being given. Huh? So here I will not write because it is meter now. So it is, I have to use kg. And if it is, they have given, it is in velocity is given in meter now. So it should be in kg. Unit should be same. So it will be what? Mass is 9.1 into 10 to the power minus 31. And what is the velocity? Velocity is already given. 6.4 into 10 to the power 4 whole square. So please find out this value first. To use calculator. So how much did you get? Hmm?
(8.25 to into 10 to the power minus 23).
8.25
into 10 to the power minus 23.
No. This value should be 1.864 into 10 to the power minus 21.
So I got 1.864 into 10 to the power minus 21.
Very good girl. What is your name?
Sir Eileen.
Very good. This is so good second. Okay, forget. Now I have to find out here H nu. See, here frequency is not given. So what we can write? We know this. So what is the velocity of light? Velocity of light is 3 into 10 to the power 8 meter second inverse. Okay? So I'll write now here 6.626 into 10 to the power minus 34 into 3 into 10 to the power 8 divided by 470 into 10 to the power minus 9. Find the value. 6.6 into 3 divided by 470. And here you bring all the value of 10. So 10 to the power minus 34, you bring it to the top. How much it becomes? 10 to the power 9 into 10 to the power 8. So 9 plus 8 is 17. Okay. And if you subtract from 34, how much it comes? 17 only. So find what here. My calculator is missing.
Sir, 4.23 to the power minus 17.
So how much it comes?
4.23 to the power minus 17.
Hey, is it correct? I didn't check. Yeah, 4.23 to the power minus
17.
So I got minus 19.
Yes, because how can you? If you divide such a large value, then it cannot be 17 now. Minus 100. Hey, what is your name? You have to somehow improve your quality. Otherwise, see, you take such a long time to do it, so much pain you have done. Your result will be wrong, dear. You please try to develop some sense of decimal. So it is this. Okay. So now, see this. So what we will write now here? So W0 is equal to H nu, na? So 4.23 into 10 to the power minus 19 minus value 1.86 into 10 to the power minus 21. Now it is a bit difficult for you to do. No problem, it's easy. See, I'll write it like this.
So it's 1.864.
Huh?
So it is 1.864.
Oh, yes. Good. Thank you. So 10 to the power minus 9, 10 to the minus 19, I take common. Okay. So it is 1.864. See, 21 minus 19, how much? 2 or not? So I'll leave 10 to the minus 2 inside and take out 10 to the minus 19 common. Now, 4.23, if I remove this one, what I will get? See, 2 decimal I will bring this side. So it is 0.01864 into 10 to the power minus 19. Subtract from this one. Now it becomes easy for you to do. So Eileen, how much you got now? Tell. So if you subtract this from this, how much you get? Use calculator.
So 4.2136 into 10 to the
So
power 19 minus 19.
W0 is equal to how much?
2136. 21136. 21136.
21136 into
10 to the
huh?
power minus 19. 10 to the power minus 19.
See. Now, dear, what they want? 1 mole of electron. Okay? This is the value only for 1 electron.
Yes.
So 1 mole of electron is equal to how much? 1 mole of electron is equal to 6.023 into 10 to the power 23. So multiply this value by this. So what you can write? W0 for 1 mole of electron equal to 6.023 10 to the power 23 into 1.864 into 10 to the power minus 90. Again, multiply this by this and subtract this positive and this is negative, so positive will be more. Fine. This equation, these calculations, sums are not difficult. Only the calculation part is difficult. So you have to be very careful in the place of decimal. Because this photoelectric equation, always you remember this is only for 1 electron. So how much did you get?
Sir, 1.122 into 10 to the power 3.
Okay. Eileen, Kanno?
Yes, sir, I got like that.
Yes. Then this is the way you're supposed to do. Okay. Then thanks for today. Bye.
Thank you, sir.
Sir,
Okay.
sir.
Let me